a computer that computes on atoms, the ultimate constituents of matter itself. In a 5 to 10-year time frame, quantum computing will break encryption as we know it today. Quantum computers are evolving faster than anyone anticipated. Well, the arrival of quantum computers could be even more historic, and physicist Michio Kaku has issued a dire warning about their potential. According to Kaku, these machines are becoming so powerful that they may be capable of bending the very fabric of reality. So, reality as we knew it was all wrong. It is the basis of all life on Earth. Quantum computing is no longer just a technological breakthrough. It's a force that could redefine science, physics, and our understanding of the universe itself. However, with such immense power comes equally immense risks. In today's video, we'll be exploring all the crazy things quantum computers are doing. Let's dive right into it. The ongoing fascination with quantum technology has made quantum computing a topic of growing interest, not only among scientists, but also among everyday people who are curious about how the world works at smaller scales. Quantum computers will change everything. When you hear about futuristic machines that can solve some types of math problems in seconds, problems that would take ordinary computers millions or billions of years, you might think of science fiction. Yet quantum research is quite real, with big companies like Google and IBM investing enormous resources to harness the strange powers of the quantum realm. But alongside genuine excitement, there are plenty of stories floating around about how quantum computers might rewrite reality, bend time, or shift us into other universes. It sounds sensational, but these claims tap into a deep and widespread sense of wonder. Quantum computing is based on some of the core ideas of quantum mechanics, the branch of physics that studies the behavior of particles at very tiny scales. We usually learn in school that a computer's fundamental building blocks, bits, are either 0 or 1. But in a quantum computer, qubits can be in many states at once. This concept, called superposition, feels almost like magic because it goes against our normal intuition. Another concept, entanglement, is when two or more qubits become linked so that what happens to one instantly influences the other, no matter how far apart they are. People often evoke the term spooky action at a distance, quoted from Einstein, to describe this effect. It's something that plays an important role in quantum computing's speed. Stories about quantum computers reshaping our lives and even rewriting the world around us have become more common in online forums, social media posts, and conspiracy theories. Some folks tie it to the so-called Mandela effect, where large groups of people remember an event or a cultural detail differently from what's in the records. Others suggest that these powerful machines might open gates to parallel universes or break our sense of cause and effect. While these stories often lack solid evidence, they reflect how quantum mechanics can push the boundaries of our imagination. This first segment will start us on a journey through some of the real science behind quantum computing, as well as the more far-reaching ideas that capture the public's imagination. People are drawn to these grand claims because quantum physics itself is so counterintuitive. Scientists struggle to explain why particles can act like waves, show up in more than one place at a time, or stay connected across large distances. It's a fair question to wonder if someday this apparent oddness could lead to phenomena that seem impossible by today's standards. As we explore these ideas, we'll look at the facts, the fantasies, and everything in between to better understand what quantum computers really can and can't do, and how all of this got mixed up with rewriting reality. Classical bits versus qubits, a friendly overview. Before diving into the mystery, it's worth taking a closer look at what sets quantum computers apart. Traditional computers rely on bits, each of which can be in one of two states at a time, 0 or 1. Picture a light switch that's either off or on, and you get the basic idea of how data is processed and stored. Everything from your phone to a supercomputer runs on these bits, combining them in huge numbers to carry out tasks. Quantum computers use a fundamentally different idea called qubits. Quantum bits. Rather than being just off or on, qubits can occupy a combination of states all at once, a property known as superposition. A simple way to visualize it is imagining a coin that's spinning in midair. While it spins, in a certain sense, it's neither heads nor tails, or it's both heads and tails. Once you measure it, it collapses into either heads or tails. In a quantum computer, while the qubit remains in superposition before measurement, it can process many possible outcomes at once. This ability allows quantum computers to explore a vast number of computational paths all at the same time, making them incredibly powerful for problems that grow exponentially with size. If you try to solve a large factoring problem on a regular computer, you might need a century or more to finish. A well-designed quantum computer could, in theory, cut that down to minutes or seconds. Another quantum feature that helps is entanglement, where qubits become linked in such a way that the state of each one depends on the state of the others. When you combine superposition and entanglement, quantum computers can do certain operations in a way that classical computers will never match. However, this doesn't mean quantum computers can outperform classical machines on every single task. They have certain niches where they excel, such as cryptography, optimization, and simulating quantum systems. But if you want to write an email, browse the web, or do day-to-day computing, classical machines are still fine. The real draw of quantum computing is its potential to tackle special problems that are too large or complex for classical approaches. Because of the strange underlying physics, quantum technologies also have high error rates and require delicate conditions. Qubits can easily lose their quantum properties if they interact too strongly with the environment, a process called decoherence. That's why quantum chips are often kept at extremely low temperatures and shielded from outside interference. Even a little bit of noise can mess up the calculations. While scientists and engineers are making fast progress, a large-scale, fully error-corrected quantum computer is still a work in progress. Despite these practical hurdles, many tech giants and governments are racing to build the most advanced quantum machine. Huge investments are flowing in, with the hope they'll be the first to show quantum supremacy, which is the point where a quantum device does something that no classical computer can realistically match. Google's Sycamore processor made big headlines by solving a specialized problem much faster than a classical supercomputer. After that, a new chip called Willow was rumored to handle even more ambitious tasks. Our latest quantum computing chip was developed to learn and evolve like the natural world around us. Willow. These breakthroughs feed excitement and speculation alike, since each advance brings us closer to a time when quantum machines might become widely usable. Rewriting. Reality. Much of the talk about quantum computers messing with reality comes from misunderstanding the weird aspects of quantum physics. Quantum mechanics is famous for phenomena like wave-particle duality, the collapse of a wave function upon measurement, and the idea that particles might be in more than one place at once until observed. When you add entanglement, which Einstein called spooky action at a distance, it sounds like the laws of nature are being bent or broken. Some people take this to mean that quantum computers might somehow break the rules of our universe. Part of the hype also involves the concept of many worlds. This is an interpretation of quantum mechanics that proposes that every time a quantum event has multiple possible outcomes, the universe splits into separate branches for each outcome. According to this view, if a qubit is in a state of superposition, it might be linked to different layers of reality. This makes some wonder if quantum computers aren't just doing computations locally, but in many parallel universes at once. Scientists who study interpretations of quantum theory might say that's an oversimplification, but it nonetheless sparks the imagination. An extension of this idea is that a powerful enough quantum machine could do more than just run calculations. It could cause shifts in our timeline, rewriting events in small or large ways. Suspicion that the device is tapping into an alternate timeline is a thrilling concept for plots. Yet it's generally not how real quantum computers are studied or built. Real labs are full of very advanced engineering concerns, like how to keep the qubit stable and error-free for longer periods. Still, media can shape how the public views cutting-edge science. For instance, hearing that Google's Sycamore chip or the newer Willow chip can solve huge problems in a matter of seconds might lead someone to believe that anything is possible, including warping reality. When headlines say quantum computers might defy physics, it's often a bit of journalistic flair. In a strict sense, quantum mechanics is still physics. It just involves rules that seem odd compared to our everyday experiences. Yet, it's natural for people to use their imaginations about technology that they've never seen up close. The workings of a quantum processor can be downright alien compared to a normal CPU. You can't just ring up your local store and buy a quantum laptop. All of this distance between the public and the actual research lab leaves room for wild speculation. Supporters of the quantum rewriting idea will sometimes cite the fact that quantum computers rely on bizarre phenomena that scientists themselves often call paradoxical. But calling something paradoxical in quantum mechanics usually just means it clashes with classical thinking, not that it can reorder the space-time continuum. A brief history of quantum mechanics and computing. To understand why quantum computers exist at all, it helps to look back at the early days of quantum mechanics. In the early 20th century, scientists like Max Planck, Niels Bohr, Werner Heisenberg, and Erwin Schrödinger discovered that, on the smallest scales, energy and particles behave in ways that classical physics could not explain. Observing electrons around an atom, for example, showed that they could jump between energy levels in discontinuous steps rather than gliding smoothly. Light, which we see as waves, appeared to come in tiny packets called photons. This new physics had rules about uncertainty and probability that defied standard intuition. Over time, these discoveries led to the formalism of quantum mechanics, mathematical frameworks describing how particles like electrons and photons behave, complete with wave functions and operators. Then, over the course of the 20th century, researchers began to wonder if they could harness these properties to create new kinds of computing devices. Pioneers like Richard Feynman speculated that to simulate nature, which is inherently quantum, you might need a computer that also operates according to quantum rules. By the 1980s and 1990s, mathematicians and computer scientists had proposed quantum algorithms that could, at least in theory, massively outpace classical computers for specific tasks. Peter Shor's famous algorithm for factoring large numbers is a landmark. On a large enough and stable enough quantum computer, Shor's algorithm would break much of our modern cryptography. That alone got governments interested, because secure communication and data protection rely on the fact that factoring huge numbers is extremely hard for classical machines. As quantum computing began taking shape, it spurred a surge of excitement. But building a quantum computer is tricky, requiring advanced control of qubits and a way to correct errors. While the theoretical interest was high, practical demonstrations lagged behind for decades due to technical barriers. In the early 21st century, labs around the world started to see real progress, and big tech players like IBM, Google, Microsoft, and others joined the race. Military and finance sectors also paid attention, given the potential impact on encryption and other strategic applications. Over the years, quantum computing has gone from a weird concept on whiteboards to actual physical machines that carry out quantum experiments. Achieving quantum supremacy was a big moment that showed the feasibility of quantum devices, surpassing classical computers for at least one specialized task: the Mandela effect and collective memory. The Mandela effect is often mentioned in discussions about quantum reality shifts. It gets its name from a large number of people who claim to remember Nelson Mandela dying in prison in the 1980s.